Hello everyone, in this video we are going to study a special kind of tree known as binary tree. A binary tree is a tree in which every node has less than or equal to 2 children. Consider this tree. Here the nodes are numbered as 1, 2, 3, 4, 5 and 6. In this tree we find that the node 1 has 2 children, node 2 has 2 children, node 3 has 1 child, node 4, 5 and 6 have 0 children. As in this complete tree, each node has less than or equal to 2 children. This is a binary tree. As another example, consider this tree. Here the nodes are numbered 1, 2, 3, 4, 5, 6 and 7. In this tree, we see that the node 1 has 2 children, the node 3 has 1 child, the nodes 4, 5, 6 and 7 have 0 children, but there is a node 2 that has 3 children. As there is a single node that has more than 2 children, this is not a binary tree. So, in a binary tree, there cannot be any node which has more than 2 children. Now, let us discuss some types of binary tree. The very first type that we are going to discuss is proper binary tree. This is also known as strict binary tree. A proper or strict binary tree is a binary tree where every node has 0 or 2 children. Thus, either it is a leaf because a leaf has no child, or it's an internal node having 2 children. Take an example of this tree. Do you think this is a proper binary tree? No, this is not a proper binary tree because this particular node has 1 child. Now let us take another example. This is an example of a proper binary tree because these nodes have 2 children, whereas the other nodes are leaves and don't have any child at all. The second type of binary tree that we are going to discuss is complete binary tree. A complete binary tree is a binary tree where each level is completely filled except possibly the last level. But if the last level is not completely filled, all nodes on last level are aligned as left as possible. Take this tree as an example. In this tree, the level 0 is completely filled as it has one node. The level 1 is also completely filled as it has two nodes. Is the level 2 completely filled? No, it is not completely filled, but it is the last level. Also, we find that all the nodes on this last level are aligned as left as possible. Thus, this is an example of a complete binary tree. Whereas, take this example of a tree. Do you think this is a complete binary tree? In this tree, the level 0 is completely filled, the level 1 is also completely filled, the level 2 is not completely filled. Though this is the last level, but we find that all the nodes on this level are not aligned as left as possible. Had they been aligned as left as possible, these two nodes would have been the child of this node and would have been cut from their original position. Thus, this is not a complete binary tree. The third type of tree that we are going to study is known as perfect binary tree. A perfect binary tree is a binary tree where all levels are completely filled. Let us take an example. Is this tree a perfect binary tree? No. It is easy to see that here, while the level 0 and level 1 are completely filled, the level 2 is not completely filled. Thus, this is not a perfect binary tree, whereas the tree that I just drew is a perfect binary tree. Here, the level 0 has 1 node, the level 1 has 2 nodes, and the level 2 has 4 nodes. Thus, all the levels in this particular tree are completely filled, and this is a perfect binary tree. Let us analyze some of the properties of a perfect binary tree. We can see from this example that the nodes at level 0 is equal to 2 to the power 0, the nodes at level 1 is equal to 2 to the power 1, and the nodes at level 2 is equal to 2 to the power 2. Thus, we can say at level k in a perfect binary tree, we have 2 to the power k nodes. Thus, if a binary tree is a perfect binary tree and has a height h, this means that the binary tree has levels from 0, 1 up to h. This means that the number of nodes in the perfect binary tree of height h is equal to 2 to the power 0 plus 2 to the power 1 up to 2 to the power h, which is nothing but 2 to the power h plus 1 minus 1. Now, suppose you are asked to find that there is a perfect binary tree of height h and you have to tell how many nodes does it have. It is quite simple. We just saw it above that the number of nodes is nothing but 2 to the power height plus 1 minus 1. Now, let us calculate the reverse. Suppose we are given that a perfect binary tree has n nodes and we have to calculate the height of binary tree, height of perfect binary tree. From this equation, we can see that n is nothing but 2 to the power height plus 1 minus 1. Doing some maths, we see 2 to the power height plus 1 is equal to n plus 1. Taking log both sides, we get height plus 1 is equal to log to the base 2 n plus 1, and height is equal to log to the base 2 n plus 1 minus 1. Thus, for a perfect binary tree of n nodes, we have the height of the binary tree as log to the base 2 n plus 1 minus 1. We are not going to prove the general case for a complete binary tree, but for a complete binary tree, we can say height is equal to the floor of log to the base 2 of n, where n is the number of nodes of the complete binary tree. Great. Why this discussion is important for us is because a lot of tree algorithms have time complexity in terms of the height of the tree. Thus, as we just saw that in best case the height can be logged to the base 2 of n. What can be the worst case of height of a tree? Let us take this example of a tree. Is this a binary tree? Yes, is a binary tree where all the rights are null. This binary tree has 4 nodes. What is the height of this binary tree? As you may recall, height is the length of the largest path from root to a leaf. Thus, in this case, height is 3. You can easily see that in worst case, height can be order of n, where n is the number of nodes in the tree. So, in worst case, if a tree algorithm has complexity of order of height, this is equal to order of n. But if we have some way to ensure that the height of tree will be very less, like in the case of a complete binary tree, we might be able to optimize those algorithms. What we saw in the complete binary tree or a perfect binary tree was the trees were quite balanced. What I meant by balance is that the heights on both the left and right sides were almost similar. Let us formally define a balanced binary tree now. A balanced binary tree is a binary tree where difference of heights of left and right subtree is less than or equal to k. In most of the cases, the value of this k is equal to 1. Let us take some examples. Let us take this tree as an example. Do you think this is a balanced binary tree if we take the value of k as 1? Let us see. We don't have to evaluate for leaves as by definition their left and right are null. So the difference in the heights of left and right is 0. First, let us consider the node number 2. For the node 2, the height of the left subtree is 0. So understand that this is the left subtree. Here the height is 0. Similarly, the height of right subtree is 0. What is the difference between height of left and right subtree? It is nothing but absolute of 0 minus 0, which is 0. So this node holds the property. Let us take the example of node 1 now. What is the height of left subtree for node 1? It is easy to see that it is 1. Now, what is the height of the right subtree of node 1? It is 0. What is the difference between the height of left and right subtree? It is the mode of 1 minus 0, which is equal to 1. This is also less than equal to 1. As all the nodes in this tree hold the property of a balanced binary tree, this is a balanced binary tree. Now, let us take another example. Let's number the nodes from 1 to n. In this particular case, first, as earlier, we can ignore the leaves as they are already balanced. Let us see for the node 4. What is the height of the left subtree for 4? It is 0. What is the height of right subtree for 4? As it is null, we can assume the height to be minus 1. What is the difference between the height of left and right subtree? This is nothing but mod of 0, comma, minus 1, which is equal to 1. So this node satisfies the property. Now let us take the case of node 2. What is the height of left subtree for node 2? It is easy to see that it is 1. What is the height of right subtree? This is 0. So the mode of 1 minus 0 is 1. So this node also holds the property perfectly fine. Now let us take the final example of node 1. What is the height of the left subtree to node 1? It is 2. What is the height of right subtree to node 1? It is 0. As the difference between 2 and 0 is 2, which is greater than 1, this is not a balanced binary tree. Now we have discussed a lot of properties of the trees, and these will help us in further defining special types of binary trees such as binary search trees. And there you will get to understand that why minimizing the height of a binary tree helps us in optimizing the algorithms. Before we discuss that in future videos, let us discuss how we can implement binary trees. As we defined earlier, in a binary tree, each node can have 0, 1 or 2 children. So it becomes logically easy to see that the 2 children for any node can be defined by a left and a right pointer for that node. So one very common way to implement a tree is using a structure of node. This structure of node holds the data that that particular node holds. In this case, we can assume it to be an integer. It also holds a pointer to the root of the left subtree. So this will be a struct node pointer to left. Similarly, it will also hold a pointer to the root of right subtree. So this will be struct node pointer to right. Now, how will we represent a tree? The tree will be represented just by the pointer to the root node of the tree. There is another way in which people can implement trees. This is commonly used for balanced binary trees. This is using arrays. Let us take this tree as an example. Here, let us put some numbers in each node and let us number every node by a particular value. Suppose this is 1, this is 2, this is 3, this is 4 and this is 5. Do note that these numbers 1 to 5 are not the data of the node, but these are just some numbers that I have assigned to the nodes. Why are they important? You will see in some moment. Now let us create an array indexed by 1. Now let us put the corresponding data for the number on its index. So the number indexed by 1 is 18, the number indexed by 2 is 1, so the data inside the node indexed by 3 is 13. Similarly for 4 it is 2 and for 5 it is 70. I say this is the representation of this tree. You may ask, why is that the case and how are we storing the left and right here? Let us see in some depth. What we realize from here that if a node is numbered x, the index of left tree is 2 into x. For example, for this case, the index of left subtree was 2 into 2, which is 4. Also, the index of right tree is going to be 2 into x plus 1. So, here the index of right is 2 into 2 plus 1, which is nothing but 5. So, this particular array implicitly holds the left and right pointers. Now, if I ask you what is the left pointer of the node 3, of the node at index 3, you will say that hey, it is going to be at index 6. As the index 6 is not present in this array, there is no left uh, child of this node 13. We can see this from here as well. The left child of node 13 is null. Great. But I ask to you that this particular implementation is mainly used only for balanced binary trees. Why is that the case? Let us take an example of a skewed binary tree. A skewed binary tree is a tree that we showed a bit earlier, where all the nodes act like nothing but a linked list. Suppose we had to represent it as an array. How many elements would we need in the array? As we have to start from 1, so there would have been a 1 here, there would have been a 2 here, and to represent this null, there would have been a 3 here as well, then 4, here it would have been 5, then 6, 7, 8, 9, 10, and so on. So you can say that to represent this skewed binary tree, we would have needed an array of size almost 16, and most of the values inside this array would be nothing but null. Suppose we have an array of integers, we would be representing it by something like -1. So for this case, let us draw a tree of size 16. So here, let us number the indexes. Okay, the node at index 1 is going to be 1. Now, what is the node at index 2? It is 2. What is the node at index 3? It is -1. Do you know what is the index of this tree? This is 4. So the node at index 4 is going to be 3. The node at index 8 is going to be 4. But you can see clearly here that all the other spaces are empty and will store nothing but -1. Thus, this is a lot wastage of space. Thus, array representation is not suitable if a tree can be skewed or not balanced. We will learn about different properties of balanced binary trees and some special kinds of balanced binary trees for some special operations in the next video. Thank you.